Let's get started with fundamental chemical laws. All right, so we're continuing our idea of the early history of chemistry. Some of the big players in history are these fundamental chemical laws. But before we get to that, for example, one of the big things that was discovered are these heavy hitters, right? Carbon dioxide, nitrogen gas, hydrogen gas, and then oxygen gas. One of the reasons is during this time, the late 18th century, and by the way, that means in the 1700s, right? So in the 1700s, combustion was being studied extensively. And if you go back to the previous video, we did mention that there was combustion being studied, but that became more and more of the hip thing to study, right? Because just like Robert Boyle started, right? This became more and more popular as time went on, right? More and more popular as time went on. And so because of that, the true natures of these somewhat difficult to identify substances at the time were actually identified. The list of known elements continued to grow and grow. More unique elements were discovered. Because up until this point, a very small number of elements were actually understood. I mean, these very basic molecules were being discovered, and we would kind of consider these like no-duh molecules in this day and age. Then we get to Antoine Lavoisier. He's French, and he was the first to explain the true nature of combustion. Right? We know that it is something plus O2. Right, oxidizing that something. Now, if whatever this is, if it contains carbon, we'll get CO2 as one of the products. If this contains hydrogen, for example, if it's a hydrocarbon, it'll contain some amount of water. Antoine Lavoisier was the first person to actually deduce this, that it wasn't phlogiston, something coming out of a burning material, that in fact it was the consumption of oxygen in that type of oxidation reaction. Same person, was also the first person to publish what we would consider a chemistry textbook. He also stated the law of conservation of mass that we'll talk about here in just a moment. Unfortunately, he died when he was relatively young, very young actually, because for a time in his life he collected taxes for the French government. And it was during his prime years as a scientist that the French Revolution broke out. And because he had been a tax collector and was associated with some of the more, I guess at this time, infamous families in France, he was executed as an enemy of the state in 1794. But one of the other things that we attribute to him is that he was the first to absolutely insist on quantitative analysis, right? When we mention Robert Boyle up here, he was the first chemist to perform quantitative investigations, right? He was the first one. He was the first one. And it became more and more popular until we finally get to this point where people are like, no, you have to have numbers. You have to have data. You have to examine this empirically. If we are going to call this a natural science, we have to use numbers. Quantitative experimentation. Lavoisier was the first person to insist on this. Now, because of this, he was able to come to some remarkable conclusions. The first one that we're going to highlight is the law of conservation of mass. Now, you'll see these kind of grayed out boxes on your notes from time to time. They're big deals, right? They're big deals. For example, the law of conservation of mass is a big deal, right? And today we understand this as the law of conservation of mass and energy, because the nature of energy was investigated and explained in more depth at the beginning of the 20th century. But at this time, right, when Lavoisier was still working, it was just the law of conservation of mass. And you guys know this, mass is neither created nor destroyed. I remember the first time that I heard this idea, it was actually on a Saturday morning science show called Beekman's World. I remember that. I used to watch it every Saturday. I thought it was super cool. But that was you can look that up if you want. Mass is neither created nor destroyed. right? You cannot create mass, you cannot destroy mass. Let's move forward, right? We were in the late 18th century. Now let's get to the early 19th century, 1808, John Dalton. That name should be pretty familiar from Gen Chem. Two of these fundamental chemical laws are attributed to him and his use of quantitative analysis. He later went on to develop his atomic theory of matter, which means atomic, used to atoms, right? He was, even though the term was thrown around here and there throughout history, this was the first time that the term atom had been picked up with any significance since Democritus first coined that idea almost 2,000 years earlier. So one of the first things that he was able to state was the law of definite proportions. And law of definite proportions, right, again, might seem obvious to us today, but a given compound, right? So let's just pick one for example. Let's go CO2. That's one that we work with quite a bit. Carbon dioxide. So carbon dioxide is a given compound. So a given compound always contains exactly the same proportions of elements by mass. And so just so we can get an idea of what this means and not get lost in the language, let's substitute a given compound with this name. Carbon dioxide always contains exactly the same proportions of elements by mass. So what does that mean? Carbon dioxide always contains the exact same proportions. It's always 1 carbon and 2 oxygens. It always contains the exact proportions of elements, meaning it's always carbon and it's always oxygen. And so what this tells us is if we don't have this exact ratio of mass between carbon and oxygen, it must be a different compound. It must be a different compound. And in fact, that is how several different pieces of chemistry equipment, high-level pieces of equipment, not the kind that we have at the high school, but more like research colleges. Chico State has some of these heavy-duty pieces of equipment. That's actually how they analyze molecules. They'll break them down and they'll tell you what the masses are by element, and so you create that ratio. And so any compound that you put in here is always going to have the exact same proportion of elements by mass. Moving on to the law of multiple proportions. So definite proportions. And I would like to point out this word, you know what the root word of this? Define, right? Definite. It's been defined. It's defined this way. The law of defining proportions. CO2 is defined as having 1 carbon, or the mass of 1 carbon and the mass of 2 oxygens. That's the definition of CO2. Now, instead of definite, defined multiple proportions. Whoa! So that means if we know that a given compound always has the exact same proportions, if there are multiple proportions, it can't be the same. It can't be the same compound, right? If I have some CO2 and I throw it into a bucket and I break down and analyze it, it's going to have a very, very specific ratio of the mass of carbon to the mass of oxygen. If I throw another carbon and oxygen containing compound into that bucket, it's going to show me a different proportion. Now, I'm going to try to give you a brief description of how specifically this law works. When 2 elements, like carbon and oxygen, some books focus on the example of nitrogen and oxygen, but it's all the same. When 2 elements combine to form a series of compounds, because there's carbon monoxide, there's carbon dioxide, like we mentioned earlier, there's even the carbonate anion, right, which has there's -2 charge actually. All right, but we have CO, CO2, and CO3, right? And so we can combine carbon and oxygen to make a series of compounds. In this case, this is a series of 3 compounds. But when 2 elements combine to form a series of compounds, the ratio of masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. And so what that means is if we have 1 gram of carbon, right? Notice in this table we're defining carbon as having 1 gram. Well, for every 1 gram of carbon, we have 1.33 grams of oxygen, right? So this table is telling me the mass of oxygen that will combine with 1 gram of carbon. But in a second carbon and oxygen containing compound, again, always having 1 gram of carbon, right? Always 1 gram of carbon. The amount of oxygen that combines with that amount of oxygen, carbon is 2.66. Notice that it's doubled. It's doubled, right? So when I go from here to here, I am doubling the amount of oxygen I have. And so this is going to indicate a transition from the first compound being CO, second compound being CO2, right? But the law of multiple proportions says that the ratio of the masses of the second element, right here, to the 1 gram of the first element, right here, is always going to be a small whole number, right? In this case, it's 2. The ratio of that to that is 2 to 1. The ratio of this, of the CO3 to the CO, would be 3 to 1. Right? So these can be reduced to small whole number ratios. And like I said, therefore, compound 1 may be CO, right? 1 carbon, 1 oxygen, and compound 2 may be CO2, right? Because we're doubling the mass of oxygen that is combining with 1 gram of carbon.